speaker, Professor Mahender Singh, who will tell us about surface null theory and related groups. So let's welcome.
Thank you, Professor Mantro, for a kind invitation. So it's a wonderful opportunity to present some observations that we made. So I'm going to talk about surface knot theory and related groups. So my title is a little misleading, so I hope I will be able to convey the right meaning. So these observations are in some recent work with my student Neha Nanda and a postdoc, Tushar Nayak. All right, so just to set the context, I will recall some very elementary knot theories just to set the tone of what we intend to do. So experts may please excuse me. Okay, so yeah. All right, so we have classical knot theory, and it has a vast generalization, the virtual knot theory. And we know that classical knots and links, one can consider them as knots and links in the thickened two-dimensional sphere. And the knot theory in the thickened two-dimensional sphere is equivalent to knot theory in the three sphere that we all know of. And virtual knot theory can be thought of as in the higher genus. Of course, here the surfaces are varying and there is more stronger kind of equivalence. So, but roughly you can think of them as knot theory in thickened surfaces of higher genus. So what is surface knot theory is basically I will be studying immersed circles in surfaces. So the genus 0 will correspond to the sphere, and the higher genus, or what I call higher genus, basically I mean the virtual setup, that will correspond to immersed circles in surfaces of higher genera. So this is roughly this slide should convey the roughly the plan. Okay, so what are braid groups? So we know braid, we are well aware of braid groups. So they are related to links in the Euclidean space. So a geometric braid is a subset of the infinite. So one can think of it as a subset of the infinite strip consisting of n intervals, which one refers as strand, consisting of and 2n mark points on the top slab and 2n mark points on the bottom slab, and with some conditions that the top and the bottom points of these strands form this complete set of 2n mark points, and the strands do not intersect with each other. And if you take any plane parallel to this, the plane R2, and if you intersect with this geometric braid, then it should meet in exactly once. So each strand intersects any horizontal plane exactly once. So this is how we can define a geometric braid. And then one need to define some appropriate equivalence, as you can imagine, because one could have different, one could perturb braids a little bit. So two braids are on the same set of 2n mark points are said to be equivalent if one can be continuously deformed into other in the strip without really creating crossings, okay, without really crossing any strands. So very well known definition. So here I have a figure. One can see that these two braids on three strands are equivalent. Okay. All right. So the beautiful thing is that set of all these braids, we can turn this into a group. So one can take one configuration and other configuration and just place one on top of the other, and then reparameterize the interval back to 0, 1, and you get this new geometric braid again in the infinite strip. And one can easily show that this is in fact a group, the Artin braid group. So this is my starting point, and then I'm for a reason I'm repeating, I'm telling all these things because I want to do a planar analog of this. So we know this famous theorem of Artin from 1925 that the braid group, the geometric braid group Bn that I just defined is in fact isomorphic to the abstract group which has this presentation. It has n-1 generators and these defining relations the far commutativity relations, and the famous braid relation. So in fact, the generator sigma I, one can represent geometrically in this fashion, the I and I plus 1 strand crossing. Okay. So this figure I will come back to later. And one can define the closure of a geometric braid just by closing the top nth point to the bottom nth point. And this is a well-defined operation in the 3 space up to isotopy, and it gives links in the 3 space. So this is the connection between braids and links. So we will talk about the planar analog of this setup soon. And the most, I consider this as the most powerful theorem in this theory of knots, which does that Alexander and Markov theorems. So every link in R3 is equivalent to closure of a geometric braid. So if I'm given, of course, every geometric braid upon closing gives a link, but the reverse also hold. And the natural question is, if 2 geometric braids gives the same equivalent links, so how are they related? And Markov's theorem tells precisely the conditions under which they are related. So 2 geometric braids with equivalent closures are related. With equivalent closures are related by a finite sequence of moves, what we call Markov moves. So the first thing is the 2 braid elements should be same as group elements in the braid group. And second possibility is that they are conjugate. And the third is that you can add an extra strand or its inverse, that sigma n at the end of one of those. Okay. So if I can relate beta 1 to beta 2 by a finite sequence of such operations, then I say they are Markov equivalent. And these 2 theorems combined tells us that the set of isotopy classes of links in the 3 space is in bijection with this infinite braid group modulo this Markov equivalence. So what we are looking for is similar kind of theorem for planar setup. And of course, there are analogs of all this theory in virtual knot theory and other generalizations of knot theory. And this is the theorem that I was really talking about, the Rademacher's theorem. So this translates this topological problem of equivalence of knots completely into the planar setup. And this idea has been exploited tremendously in the literature, and because it's always easy to work with diagrams on the plane rather than topological equivalence in the 3 space. So the theorem tells that 2 links in the 3 space are equivalent if and only if any link diagram of one can be transformed into any link diagram of the other by a finite sequence of planar isotopies and the 3 Rademacher moves. So we all know the moves. So the first Rademacher move is removing the king. The second Rademacher move is just sliding up the 2 strings. And the third is sliding the third one underneath one crossing. And this observation I want to make here, that the knot diagrams on the plane, there is a correspondence between knot diagrams on the plane and knot diagrams on the 2 sphere. So this correspondence is also used to justify my first statement that knot theory in the 3 space is equivalent to knot theory, classical knot theory in the thickened 2-dimensional sphere. So so this diagrammatic approach will also be helpful to us in the planar setup. So now, this is the question that I want to address. So is there a planar analog of Artin braid group and classical knot theory? So the answer is yes. There could be some other candidate, but we know of one, so that I want to discuss now. So this work goes back to Khovanov's paper on what he called doodle groups in 1997. So he considered a configuration of n intervals in the infinite strip R cross 0, 1. So again, it's the same setup as classical, Artin braid groups. So you fix n mark points on the top line R cross 0 and unmarked points on the bottom line R cross 1. And consider strands of this form that each strand intersect any horizontal line exactly once. And second important point is very important, that no 3 strands have a point in common. So no 3 or more strands meet at a point. So triple points or higher intersection points are not allowed here. The reason is if I allow triple and higher intersection point, then I can always separate them out. So this is crucial. So we consider configurations of this kind. And again, we can, similarly as in case of Artin braid groups, one can define an equivalence relation here. So again, I say that two such configurations are equivalent if one can be deformed into other by a homotopy of such configurations, preserving the endpoints. And an equivalence class of such a configuration I called a planar braid. So some authors call it planar braid, and but I prefer to call it twin because it's short. And also many papers, Khovanov himself referred it as twins. So I just stick to the word twin. All right. So let us see what should be the basic twins. So again, fix an integer n bigger than equal to 2, and consider this again endpoints on the top line and endpoints on the bottom line, and consider this configuration where I and I plus 1 cross at one point. So this I call the basic twin, and one can check that the set of all these basic twins, n minus 1 of these basic twins, they satisfy these relations. That is Si square is 1. And that's, look at the dotted blue line. If I cut along this, then I have Si and Si square. But my equivalence allows me to create double point, not triple point. So I can slide them off and I get Si square is 1. And again, by isotopy, I can, if I and j are far apart, then I can move ith and jth crossing easily up and down. So that I am allowed. So I have the relation that Si Sj is same as Sj Si whenever I and j are far apart. So what I call, the geometric twins or geometric braids satisfy these relations that the squares are 1 and they have the far commutativity relation. And in fact, one can again define a binary operation on the set of all such twins, just like what we do for braid groups, placing one twin on top of the other and reparameterizing the interval. And Khovanov showed that this twin group is in fact generated by these basic twins S1, S2, Sn minus 1, and they have these defining relations, and these are all. There are no more defining relations. So this we refer as a twin group or equivalently planar analog of the braid group. So far so good. So what should be now the topological analog of this? So I have got a group which I call the planar analog of the Artin braid group. So what should be the geometric objects? Analog of the knots. So that I will come in a moment. So before that, I want to point an important subgroup of this. So notice that there is a natural map from the pure, from the twin group to the symmetric group, which map this, fundamental twins into I plus 1, or equivalently, if you take any twin, then it gives you a permutation of top and bottom point and map it to that permutation. All right. So the kernel of this, we can define analogous to pure braid group, and we call it the pure twin group. And it is a non-trivial group. For example, one can see that, look at this configuration that I have drawn here. So I have this Si, if I cut just below the first crossing and then Si plus 1, and that I have repeated thrice. So it is Si plus 1 cube. And this is a non-trivial element because as you can try to see that if I want to straighten these strands, so I will have to create triple points. But triple points are not allowed in my equivalence. So this is indeed a non-trivial element of the pure twin group. And it turns out that this pure twin group is hard, presentation of this is hard to describe. So far we don't really know a very nice, clear presentation of the pure twin group, but there are we have some observations. So like for instance, with using the Reidemeister-Scher method, for example, one can show that the pure twin on 4 strands is a free group of rank 7. And of course, pure twin on 3 strand, one can easily show that it is the infinite cyclic group, in fact, generated by S1, S2 to the power 3. And a recent result of, I think, Gonzalez and Medina Roque, they showed that pure twin on 5 strands is actually a huge group. It's a free group of rank 31. On 6 strands, it's a huge group, which is a free group of rank 70. Free product with free abelian group of rank 2 with 20 copies. So it's a very special cases are known, but in general, we don't know the full description. However, we can find the rank of these groups, some bounds on the rank of this group. So it follows from the result of Bijon, Welker, dating back to 1995, and some observations with Valery Bardakov and Andrei Vesnin in our recent work in 2019, that the rank of this pure twin group can be bounded like this. So we use the Reidemeister-Schreier method, so it's not very effective here, but the lower bound one can get from the work of Bijon and Welker, and what they use is the homology of this group PTN. And quite interestingly, this group PTN also has a configuration space model, just like the pure braid group. So in fact, PTN, one can think of it as a fundamental group of triple complements of triple diagonals in the Euclidean n space. And this kind of configuration spaces, a lot of people have studied, and their homology is in fact known. So by looking at the abelianization rank of the homology, first homology, one get this lower bound. So as one can see, the rank is already exponential. So it seems a precise presentation seems a little difficult at this point, but the evidence in low dimension, I mean, the low number of strands suggests that the pure twin is in fact is a right angle Artin group. So we believe that pure twin group is a right angle Artin group. And the conjecture of course holds for up to PT7. But we don't know how to go about this in general, because the rank is grows exponentially. Yeah, so now coming back to the topological setup. So I defined a pure, and I defined a planar analog of the Artin braid group, which I call the twin group. So now what is the topological analog of knots here? So the story goes back to Fan and Taylor and their paper. I think it's a conference proceeding article dating back to 1977. So what they were interested is finite collection of simple closed curves without triple or higher intersections on the two sphere. And they have obtained quite amusing results. So using this configuration of circles, they obtain some commutator identities in free groups. So I will not get more into that. But this idea, their work was refined in the same paper of Khovanov, where he extended this notion to finite collection of immersed circles without triple or higher intersections on closed-oriented surfaces. So Fan and Taylor were restricting to simple closed curves on the two sphere, and Khovanov considered immersed circles on arbitrary closed-oriented surfaces. And he defined, of course, one need to have an appropriate equivalence here. So we say that two such collections, delta 1, let us say delta 1 and delta 2 on the surface S are equivalent if there is a homotopy from the collection of curves representing delta 1 to the collection of curves representing delta 2, without which doesn't create any triple point throughout the homotopy, the expected definition, because we just want to avoid triple points. And an equivalence class of such collections we call a doodle on the surfaces. So this is where this term doodle stand for. So these doodles will be my analog for planar knots. So I hope if there are any questions, please let me know.
Yes, I have a question. Possibly, well, we have Higord diagrams and Zinger moves for Higord diagrams. We have Reidemeister 2, but we don't have Reidemeister 3. So possibly we can try to encode some Higord diagrams by using doodles plus something, or doodles or twins.
Yes, yes. Okay. Yes, I think yes. Yeah, exactly. We are just avoiding triple point. We don't have Reidemeister 3 here. Yeah.
Yeah, and so for Higord diagrams, we have two collections of curves, so no way to get triple points.
Yeah. Yeah. All right. Thank you for the comment. All right. So I have got planar analog of my knot or link. All right. So here are two examples of doodles that I have drawn for you. So like this, the first one you can call a Borromean doodle, and the second one you can see just a one component doodle, and you can't really simplify this. Okay, you will have to create a triple point. So Khovanov in his the same paper, that's a transactions paper, he proved an analog of the Alexander theorem that every doodle for the two sphere. So every doodle on the two sphere is equivalent to closure of a twin. The proof is not very hard, but not very hard. One can actually go through this easily. But for a long time, the Markov theorem was not really known, and it was proved by Konstantin Gotin, a young graduate student from Sobolev Institute, I think student of Andrei Vesnin. So he proved an analog of Markov theorem for doodles on the two sphere. So he showed that two twins have equivalent closures on the two sphere if and only if they are related by certain Markov moves. So since I don't need those moves, I'm not going to state those moves here, but quite interesting moves. And therefore, in view of theorem of Gotin and Khovanov, one have this analog of the statement that I made for classical knots. The set of isotopy classes of doodles on the two sphere is in bijection with the infinite twin group modulo the Markov equivalence. All right. So this completes the what I roughly call genus 0. So I had classical Artin braids, classical knot theory. Then I have twins and doodles, and there are Alexander theorem, Markov theorem. We have a recipe, so one could look for invariants of doodles, and there are some recent works. In fact, Khovanov himself, in his paper, he defined what he called the doodle group, the fundamental group, and the construction involved the combinatorial structure of these immersed circles. And I think it has not been really exploited further. So there is a lot that can be done there. And a recent work of Christopher Roque and I think they are a group, they have shown some analog of Alexander's polynomial for doodles using some perturbation of the Tits representation. So recall that the twin group is a right angle Artin group. So every right angle Artin group has a faithful representation, the Tits representation into GL of the same rank. And using some perturbation of this representation, they construct this Alexander invariant. And also Bartholomew and Roger Fren, Saichi Kamada, Naoko Kamada, they have also constructed some invariants, some coloring invariants for doodles on the, I think on higher genus case that I'm going to talk about now. So we have done, we have this picture of classical knot theory and the Artin braid groups. Then we have doodles and twin groups. Now let us move to the virtual setup. So I will recall briefly what are virtual braid groups, because the theory goes quite analogous to this. So Artin braid group has a natural extension, what you call the virtual braid group VBN. And this, of course, experts know this is the right group for the virtual knot theory, which plays a role what Artin braid groups play for classical knot theory. So as an abstract group, this group has a presentation which has the generators sigma 1 to sigma n minus 1, rho 1 to rho n minus 1, with this set of defining relations. So a way to remember this is the sigma i's are precisely the braid generators. So they satisfy the braid relations, the far commutativity and the braid relation. The rho i's satisfy the symmetric group relations. Okay, so rho I squares are 1 and rho I rho j commute for whenever they are far apart, and the braid relation. And then there are these mixed relations. So of course we want rho I and sigma j's to commute when they are far apart, and there is a mixed relation. This mixed relation refers to, topologically, it will refer to sliding, I mean, an arc over a handle. You can just move it over a crossing on the surface. So geometrically, the generators of the virtual braid group can be represented as equivalence classes of configurations of this type. So we have this configuration of strands on the plane, and you have this kind of crossing where you have over under information, what we call classical crossing. And then there are this other kind of crossing which we decorate by a circle around, and we call virtual crossing. And the two configurations here are equivalent if one can be deformed into other by planar isotopies and a finite sequence of following moves. All right. So the moves are the classical Rademacher 2, the Rademacher 3, and the virtual Rademacher 2, Rademacher 3, and they're the mixed move. So this mixed move, if you have observed the generators, where I have set up the generators, and the mixed relation, you can see that this mixed relation is exactly the third diagram. And now, so that was just algebraic aspect of the virtual side. Then what is the topological aspect? So the theory actually was developed in this pioneering work of Lou Kaufman in 1999, where he introduced virtual knots as equivalent classes of set four valent planar graphs. So his motivation was from realizing every Gauss code as a Gauss code corresponds to some knot. So that's how I think he came up with this. And where each vertex is either a classical crossing or a virtual crossing under the equivalence which is generated by the following planar moves. So moves, as you can see, the moves are exactly what I showed in the preceding slide. But of course, now here I am talking about these graphs or these diagrams on the plane, so I can also remove the kinks. Okay, so having done this, one can define the closure of a virtual braid on the plane. And notice here that the closure of a virtual braid on the plane make perfect sense in terms of the, in view of the equivalence defined. Okay, so it doesn't really matter which side you close up, because you have this, the mix relation, which allows you to smooth the slide. So the detour move, okay. So therefore closure make perfect sense. And the closure of a virtual braid is actually a virtual link. So this is how we define virtual link. And Kamada in his paper in 2007 proved Alexander and Markov theorems for virtual knot theory. So now we have, if you go back to my first slide where I had this picture of a thickened two-dimensional sphere and thickened surface, then genus 0 case, we have Alexander-Markov theorems. For the planar analog, we have Alexander-Markov theorems. Now in the higher genus or the virtual setting, we have Alexander and Markov theorems. And now we want to have a planar analog of that. So I think the last part of my talk will be about that. Okay, so before going to that, let me just for benefit of audience, try to convey that virtual knots, although Lou Kaufman has defined virtual knots as a purely combinatorial graph theoretic manner, but they do have a nice topological meaning, and they can in fact be viewed as knots in thickened surfaces. So just I will show two slides on that. So virtual knots are as stable equivalence classes of knots in thickened surfaces. So suppose if you have a compact oriented surface and D a classical link diagram on a surface. So if you take two such setups, so F1 D1 where F1 Fi Di, where Fi is a surface and Di is a classical link diagram on that, then I say the two are equivalent if there is a compact oriented surface, a third surface, okay, F3 possibly a third surface, and an orientation preserving embeddings of F1 in F3 and F2 in F3 such that their images FD1 and FD2 of these two diagrams in the third surface, they are related in the classical sense. Okay, they are related by classical Rademacher moves. Okay, and we say that two such pairs, FD and F prime D prime, are stably equivalent if there is a finite sequence of such pairs. Okay, so remember that you may not be able to show that F1 D1 is equivalent to F2 D2 directly, but we should be able to find a finite sequence. So the equivalence generated by this kind of, by this tilde. So we say that, sorry, two pairs FD and F prime D prime are stably equivalent if there is a finite sequence of surfaces with the classical link diagrams on them, so that they can be consecutively equated to each other in the above sense. For instance, you take the torus, and in the torus, if you look at the torus, then this or not, if you look at the left picture and this meridian, they are stably equivalent in this sense. So the diagram shows that they are stably equivalent as virtual knots. And the theorem of Kartha, Kamada, and Saito from 2002, and Kupperberg, although the statement is a little different, so but I have combined this here, around 2003, they show that virtual links are equivalent to stable equivalence classes of links in thickened surfaces. So in fact, Kupperberg showed that you can find a minimal genus surface and a unique representative there. So that is what Kupperberg's statement. So therefore, we do have a very nice topological interpretation of virtual knots as genuine knots in thickened surfaces. So this is now we want to, I want to look at what should be the planar analog of this setup. So here is the second question. Is there a planar analog of virtual braid group or virtual knot theory? And the answer is yes. So there is a very natural choice. So we already constructed a planar analog of the Artin braid group, the twin group, and it suggests that we should do something with that group. So let us start with this setup. So consider configurations of n intervals in the strip consisting again of n mark points on the top line, n mark points in the bottom line, and with the following property. Each strand intersect any horizontal line exactly once, the natural condition. No three strands have a point in common. Okay, so first two conditions are exactly the conditions of definitions, conditions involved in the definition of a twin. And the set VD of all crossings of D consists of transverse double points of the diagram D, where each crossing has a pre-assigned information of being a real or a virtual crossing. Okay, so real crossing I denote the usual way, and virtual I just decorate it with a circle. Okay, so only the third point is an addition to the definition of a twin. And we say that two such configurations are equivalent again in the same fashion if one can be obtained from the other by planar isotopy and following planar Rademacher moves. So first figure is planar analog of R2 move, and second is planar analog of virtual R2, virtual R3, and this is the mixed one. The one on the right hand side is the mixed one. Okay, so you can see it's quite parallel to what happens in virtual knot theory. So in case of virtual knot theory, I had this crossing where real classical crossing where over and under information was there. But here, I mean, these are immersions, so we don't really have over under information. So we just write them as in this fashion. An equivalence class of such configurations we refer as the virtual planar braid, or in simple terms, virtual twin. And here are the fundamental virtual twins that should lead us to the corresponding group. So for each n bigger than or equal to 2, let Si denote this configuration, one on the left, and rho I denote the configuration which on the right. So Si is again I and I plus 1 strand cross, and the crossing is the real one, and rho I is the crossing is the virtual one. And keeping the definition, so let me go back to that slide. So keeping these 3 points in mind, one can see that this set of S1 to Sn minus 1 and ρ1 to ρn minus 1 satisfy these conditions just by looking at the equivalence. So Si square is 1 because I'm allowed to slide one arc over the other. Ρi square is 1, and I have this braid relation for ρi, right? Because so for remember I'm allowed to have virtual triple points, not the real triple points. Classical triple points are not allowed. Okay, so that allowing triple point means having this braid relation for ρi's, and again for commutativity of ρi's and si's is sort of obvious because of isotopy. And the third one is the mixed one. So I should be able to slide the virtual string over the classical crossing. Okay, so this is planar analog of the virtual mixed move for virtual knots. Okay, so these identities follow just from our definition of equivalence. And what we observed in Neha, that the set of all virtual twins on n strands form a group with the usual product of placing one virtual twin on top of the other and reparameterizing the interval up to isotopy. And this has a presentation with generators, what I just showed in the preceding slide, the SIs and the ρi's, and the relations are exactly what we saw in the preceding slide.
So, but what is this theorem? Isn't it a definition?
Yeah, it's not really, it's just a simple observation, basically. Yeah, you are right. So main theorem will follow later. So it's just a definition in some sense. All right, so this SIs and SI square is 1, SI is a commute, okay? And ρi satisfy the symmetric group relations, and then the mixed relations. All right, so this we call the virtual twin group, the expected definition, and we claim that this is the right group that should serve the purpose of group for virtual analog of planar analog of virtual knot theory. Okay, that means this is the group that should fit into the Alexander-Markov theories for virtual doodles. So this idea of virtual doodle was thankfully this has already been done in recent works of Andy Bartholomew and Roger Fens, Seiichi Kamada, and Naoko Kamada. So they have been studying this. They have been extending ideas of Khovanov and the original ideas of Fen from purely topological perspective. So let me state the definition. So a virtual doodle diagram is an immersion of disjoint union of circles on the plane, okay, with finitely many real or virtual crossings, so that there are no triple or higher real intersection points. Remember that I'm allowed to have virtual triple intersection points because that is what is a virtual Reidemeister move 3 is allowed. Okay, just like what happens in virtual knot theory. So I have recalled the virtual and real crossing for you. Here is an example of a virtual doodle. One can actually see it on a surface. So the Kishino virtual Kishino doodle. And two virtual doodle diagrams are equivalent if one can be transformed into other by planar isotopies and finite sequence of following moves. So the moves are the expected moves. One should be able to remove a kink. One should be able to slide one arc over the other. So that stands for the classical moves. And then the virtual moves, because I'm allowed to have virtual triple intersection points. So I have the virtual R3, virtual R2, and of course, virtual R1. And then there is a mixed move. Okay. So an equivalence class of virtual doodle diagram is called a virtual doodle. All right. And what they showed in the same paper is that there is a bijection between the set of virtual doodles on the plane and the set of stable equivalence classes of doodles on surfaces. So this theorem is exactly similar to the theorem for virtual knot theory. Is this more or less similar argument, and therefore one expect that similar argument should work for virtual twin groups, and it indeed works. So what the only effort that was needed in was getting the Markov moves. Okay, but one can, but it more or less one can imitate the process what happens in virtual knot theory. So this is the observation with Neha that we made, that every virtual doodle on the plane is equivalent to closure of a virtual twin diagram. So recall the virtual twin diagram that I defined a few slides back, the three conditions, and two virtual twin diagrams of the plane have equivalent closures if and only they are related by a finite sequence of Markov moves. And in fact, the Markov moves are right here. So one has planar analog of left stabilization, right stabilization, exchange, and left exchange, right exchange. And one can easily check by just drawing some diagram that at least one way is quite pretty straightforward, that if you close up, for instance, if you close up, look at the M2 move, of course, if you close up alpha inverse beta alpha, then you should get beta, okay? And if you have beta SN, okay, the SN move, and then you close it up, then what you can remove the kink, okay, and therefore it is equivalent to beta. Similarly for the virtual one, and the left stabilization also similarly you can obtain. So direct, just drawing some diagrams of these identities, one can show that one way implication follows easily, but the other way requires some effort, and more or less we have to translate, we have to prove analogs of planar analogs of established planar analogs of the argument, what happens for virtual knot theory to prove the converse part. So I will not really get into the proof of this. So now again, so we have a nice setup. So we have virtual planar analog of virtual knot theory also. There is a nice group, what we call virtual twin group. Okay, and this virtual twin group again has a natural surjection on to Sn. Send each Si and rho I to rho I itself. Okay, because the symmetric group presentation is right there, and this kernel of this is what we call the pure virtual twin group. And quite interestingly, we this pure virtual twin groups turns out to be a very interesting group. This is an irreducible right angle Artin group. So the pure virtual twin group is an irreducible right angle Artin group. And in fact, one can write down the precise presentation for this. So it is generated by these generators, lambda ij. I will show them in the next slide what lambda ij's are. So they are right here. So lambda ij's, it looked quite similar to the pure braid generators of the pure braid group. So if you recall, that generators of the pure braid groups are, it start from J, goes over I, and then wraps around I and then come back over. So it's quite similar to that. And the relations are, these lambda ij's commute if and only if all the indices are different. Okay, so it's a right angle Artin group. And if you want to identify it with something familiar, so if you look at the set of all transpositions in the symmetric group and look at the commuting graph of that. So the corresponding graph for this right angle Artin group is precisely the commuting graph for the conjugacy class of involutions in the symmetric group. I mean transpositions in the symmetric group. Because I want lambda ij to commute with lambda kl if and only if all ij kl are distinct. Okay. And in fact,
excuse me. In the relation lambda ij, lambda kl is equal to.
Oh, okay. Yeah, it's commuting. Sorry, I'm sorry, it's missing.
Lambda kl, so, lambda ij.
Yeah. Lambda kl, lambda ij.
Thank you.
I'm sorry about it. Yeah. Thank you. Okay, so the relation is lambda ij, lambda kl equals to lambda kl, lambda ij. Okay, whenever ij, kl are all distinct. Yeah. And Yeah, so, and furthermore, this center of this group is, we have shown the center of this group is also trivial, and we have a complete description of automorphisms of these groups. So let us not get into those algebraic things. So I think I'm more or less on the last slide. Yeah, so here are some open ends. So compute computable invariants for virtual doodles. So there are some there are some invariant which are already known, as I said already in this talk. So for instance, fundamental group of a doodle is already defined by Mikhail Khovanov. And in fact, he defined it for doodles on a surface. But there is a catch, one need to be careful here. He defined it for a fixed, a doodle on a fixed surface, but certainly that's just a representative for a virtual doodle. So one need to do some checks, but for sphere, it is quite a neat result. So he defined this group and in fact compute it in some cases, but nothing more is known about it. And there
Excuse me, and don't we have a gradient descent algorithm just undo second Reidemeister moves whenever possible? And won't we get a unique minimal representative for all those objects?
Sorry, excuse me, could you repeat, please?
Well, we can try to do some gradient descent algorithm, just undo the bygones. So let's undo the bygones whenever possible. Mm-hmm. So we can undo the bygones and try to apply the diamond lemma to get a unique minimal Reidemeister. So by bygones, I mean possibly something when we don't have any triple crossings inside. So this is a bygone.
Yeah.
So we can try to undo it and get a unique minimal representative. Is the minimal representative unique for twins?
Yes, for twins it is unique, I think. Yes.
Well, okay, and for doodles, I think it should be almost the same.
Yes.
Don't you try to do it for doodles? I think it should be not so hard.
Yeah. So your comment is in connection with the fundamental group or what?
No. I'm just asking about the uniqueness of the minimal representative. Yeah, I think it should be unique.
Mentioned that in his work. Yes.
Okay, so if we have a unique representative, so why should we care about invariants? So we can just undo and get a unique representative, which is in some sense a complete invariant. So why do we care about invariants?
Yes. So perhaps I think I'm a little confused with this.
So we have a unique. Well, if it is not unique, so I need an example. Mm-hmm. So what's wrong? I mean, just try to apply the diamond lemma as we do for flats, for example, for virtual flats. Flats are much more complicated than doodles because there is some third Reidemeister move. The only thing we don't have is for flats is the over-under structure. Well, and there are some other.
Perhaps I'm mistaken. I think I'm mistaken here. I think minimal representation is an issue here. Yeah, because otherwise, what's the point in defining a whole fundamental group and all these things?
Well, it's strange. I wrote some questions on the chat line, so please answer. And also I have so the main question is about the uniqueness of the minimal the minimal representative. So please think of that and try to answer that, and please answer the other questions I wrote on the chat line.
Can Sn be calculated explicitly?
So what did you calculate explicitly?
Sn, what is Sn? So Sn, the generator of the twin?
Well, I don't know. Well, it's not my question.
My notation in my notation, Sn is the generator of the twin group. So is the question from Barry. So I don't understand this question. What do you mean by Sn be calculated explicitly?
It's not my question.
Yeah, so I think we can use G and K to study the configuration space of twin OIs. So yeah, I don't know the groups G and K. So maybe, yeah. Okay. So you mean you want to, using the groups G and K, you want to propose a configuration space model for twin groups? Is that you mean by this?
Yes.
Oh, I see. Okay. Yeah, yeah. Quite possible, because for pure twin group, as I said, there is already, it's complement of the triple diagonal. So
yes,
it's
sure.
Yeah, yeah. Okay.
Yeah, okay. So let's answer the remaining questions.
So what about Hegel diagrams by using doodles or twins? So I don't know. So
well, we should try. So otherwise, doodles are very easy. So so we should look for something more interesting. So, for
yes.
example, how can we swallow one thing by another thing? So
yeah.
this move, yeah, for Hegel diagrams. So it would be nice if it would be nice to represent Hegel diagrams by words, and actually doodles are words. Well, twins are words, so it would be nice.
Yes.
Okay, let's go further.
Actually, there is an approach to frame knots by using frame braids. One can use it to get Kirby moves. What about doodles? Twin singer moves. Yeah. I think, yeah, maybe it can be done. So there are many questions. So one can think, try to bring ideas from knot theory into this thing. In fact, we have been thinking about cablings of twins and so on, but not much success.
Well, and actually we can define indices. I think it would be much easier for doodles, but of course, try to define a minimal representative. Try to look at whether minimal representative is unique for. Is the minimal representative for doodles? Oh, yes, one more question about Legendrian knots. So possibly we can look for how to
yeah, possibly we can define the indices of crossings for doodles. Yeah, okay, possible. Yeah. Yeah, so you have very interesting topological questions. So what we have been doing is we have been studying purely the group theoretic aspect of this, except Alexander-Markov theorem, we did not really look into the invariants and other things. But of course, yeah, there is a whole lot of things that can be asked. So by index, I mean some label which does not change under moves. Yeah. In the same index. Yeah, I think one can define this. There should exist a projection from the virtual object to classical object similar to parity projection. From virtual knots to classical knots. And from virtual braid to classical braids, yeah. Right. In fact, on the other side, I want to make a comment. In fact, I don't know whether the twin group sits faithfully inside the virtual twin group. We have still not been able to prove this.
Well, I think a projection can give rise to that.
I see. Okay. I see. And also, so whether this doodle theory sits faithfully inside the virtual doodles, that question remains.
Well, I think we should project. I think it should work.
I see. Okay. Okay. Thank you. So I guess not unique. Okay. Is minimal representatives for doodles unique? Yeah. Actually, I think I was mistaken. It's not unique. Yeah. Yeah. And also, I don't know if any audience has seen paper of Khovanov. So he defined this fundamental group quite combinatorially. So from this configuration of doodles on the sphere, using the vertices and arcs and the regions created, he defined a complex. And thus that complex is unique up to simple homotopy type. And the fundamental group of that, he then proved that it's an invariant. So it doesn't look very natural, so but maybe somebody has some insights into that, so I don't know.
Okay.
It's 10 o'clock.
Okay, are there any further questions? Well, if it's not the case, so thanks for the talk. Just to remind that tomorrow I give a talk at the seminar by Lou Kaufman and Roger Fan. So you can ask Son John about the details. Okay.
So these details are available on the website of this yours.
Of their seminar, I think, because they use various password, so new passcodes for each time. So I think it's better to look at their seminar, Kaufman and Fan.
But is your seminar series, these talks are recorded somewhere, because there are time zones sometimes?
Well, as for Kaufman and Fan, ask Kaufman and Fan. As for our seminars, yes, they are recorded. Yes.
Oh, so are they available to public?
Ours,
no.
Okay.
I mean, I will upload this video on the YouTube without, but one can watch this video with some links. Without links, someone cannot visit this.
Okay. Thank you very much. So.